past and present. So here's where I'm calling from this morning. This is beautiful Hobart. My office is just at the back end of this ship here, looking out over the harbour of Hobart with the city behind it. We have offices all around Australia, but this is the Hobart office. And you'll remember that Tasmania is just based in temperate waters to the south of mainland Australia. And Hobart's a city of about 200,000 people or so. But lots of marine science going on in this area. Quickly going to cover today how I got interested in marine heat waves and what's the motivation for me. Then we'll talk about what are marine heat waves, and I'll provide some advantages of a definition. And these are going to raise topics that you'll hear about throughout the week. But in particular, I'm going to emphasize that much of this progress would not have been possible without a unifying definition. And I'll conclude with some thoughts about where next in marine heat wave research. So why did I get into it? Here's a picture of Antarctica, and the location that I've circled there is where a very deep ice core has been extracted. And from the bubbles in the ice core, you can extract proxies for carbon dioxide concentration and temperature over the past 400 or 800,000 years, depending on which ice core that you use. And when you look at that history over that past 500,000 years or so, you can see there are big fluctuations in temperature and carbon dioxide. And when you look at it this way, it just thinks, yeah, the world goes through very big oscillations and maybe climate change is nothing particularly special. But if you plot this data in a different way, and you actually plot the temperature against the carbon dioxide concentration, for about the last 800,000 years, the climate system has oscillated back and forward between glaciation and deglaciation in the blue and red portion of the graph here. But we're currently sitting so far outside that historical experience. In 2024, we're up at around 423 parts per million of carbon dioxide. And thanks, keep going. And so it's a really different space that we find ourselves in. And so that's a pretty concerning thing for everyone who uses the planet, and that's all of us. And so in the areas where I work, it's really apparent that the future will be really difficult for people. It'll be very different to it's ever been in the past. And that means people's experience in managing activities that humans rely on is going to be more and more difficult. And generally, I work in resource management, like fisheries and aquaculture, and we need to make decisions that are generally okay, even if the details change, based on the best information available at the time. And that's now a very difficult decision space because of this rapid climate change. We need to learn as fast as we can. And we learn as fast as we can in two ways. We can learn faster using models, we can learn faster using experiments, and we can learn faster using observations. But each one of those approaches has a strength and weakness. And so in particular, models, we don't always understand the process and the mechanism. When we run experiments, the scale of the experiment and the factors that we can include are limited. And when we go to observations, we generally don't have very much replication. And so how are the ways that I've tried to learn faster in my science? And the first one is with spatial contrasts. In a very rapidly changing ocean, lots of warming, there are places that are warming particularly rapidly. And some work I did about 10 years ago identified the 20 or 30 spots in the ocean that are warming most rapidly. And these are places where we need to do adaptation most quickly. And have a look at where some of these places are. There's one off Southeast Australia where I work, another one off Southwest Australia, and off the Northeast United States and Eastern Canada. Those are three spots where people who have become very prominent in marine heat wave research got their start. And that's because they're working in these very fast warming areas where you had to pay attention to rapid temperature changes. This comparative approach then lets you look across and use variation across the planet to understand and learn faster. The second way to learn faster is through temporal contrasts. And so, for example, looking at what happens in El Nino or La Nina years. And that's a really good way of learning very quickly about how a system operates. And so with regard to climate then, we're going to see both shifts in the mean condition, which is where these hotspots are, as well as the extreme events and the spatial and temporal contrasts. And so under a future climate in these rapidly warming areas, we're going to see a fair bit more in extreme events, like cyclones or storm surges or deoxygenation events and marine heat waves as one of those examples. So then what does that mean about marine heat wave research? That came in, for me, it came in as an example of extreme events and how we're going to actually learn to manage those. Because I'll just go back a couple of slides to one that I wanted to show here. If you only pay attention to long-term change, then you're following change in the dotted line. But with extreme events, you get these bumps and wiggles along the journey to the future. And I became particularly interested in marine heat waves as an example of a window into the future. And so this marine heat wave here that I've indicated as marine heat wave A is actually giving us a look at what the average temperatures in the ocean might look like in another 30 years or so. And so that's a way of learning faster. By using that temporal variation, I'm able to learn faster about the future and help people think about how to operate differently. And so I think it's really important that you be able to put together both long-term change and extreme events when you're thinking about the future. So the short history of marine heat wave research. Beginning probably in the early 2000s, there were various reports of hot water. And particularly, I think some experiences in the Mediterranean in about the year 2003, really people began to take notice of really short, sharp events. Then there was a series of events that happened at about 2011 or so. Western Australia had a very strong hot event. There was another one in the Northwest Atlantic off Portland, Maine area, Gulf of Maine, and then another one in the Northeast Pacific called the Blob. And so areas with very active marine research encountered one of these extreme events right off their coasts. That led us then to thinking about, well, what is a marine heat wave? And so it was 2016 that a first, call it a common definition of marine heat waves was proposed. And since then, we've seen lots of comparative work. We've looked at attribution. There have been studies looking at global trends, evolution of categories, looking at real-time tracking of marine heat waves, through to prediction and forecasting, which became possible more widely in about 2021. And I think the focus over the last couple of years has definitely been on adaptation, planning, and interventions around marine heat wave occurrence. I'm going to go through each of these in a bit more detail now, but for me, that's the potted history of where this field has come from. It's fairly new, but we've always had hot events in the ocean. They just haven't been described in this way. So I got into this with a group in about 2014 called a Marine Heat Waves Working Group. And this was initiated out of Western Australia, which had a really hot event in 2011. And people there were working with atmospheric scientists who were also struggling with how do we define heat waves in the atmosphere. And so since then, this group has got together about 5 times or so, and colloquially, it's the Marine Heat Waves Working Group. And so we maintain the Marine Heat Wave Tracker and get together every now and again and mock up things that we're going to work on together to advance this field. And I suggest that during the week of the conference, class, that you're doing something like this with your reading. You know, Chuck's put a bunch of PDFs into the file that you're looking at, and they actually represent different elements of what marine heat waves publications work on. And so this was an example I used to keep track of the work my group was doing. On the left-hand side, we have a couple of publications that talk about classification of marine heat waves. Moving to the right, there's a publication that describes the code use. Moving on the left-hand side, then there are a range of process studies that talk about how marine heat waves evolve. And then a set of synthesis or review studies that are very commonly cited that put together global or synoptic pictures of marine heat wave events. Moving across to the second column, there's been a great proliferation of regional studies where we really try and understand how a marine heat wave works in a location and what its impact is on seafood or through to people or through to communities. There have also been biological studies with particularly looking at what are the impacts on the biology of a region, sometimes experimental work, studies looking at issues with data quality, how long should a baseline be when you calculate a marine heat wave and things like that, observation work of real-time subsurface monitoring of heat waves, socioeconomic impacts, and finally a suite through to forecasting. And I think if you, through the week, try and make yourself a mind map of where this literature sits, it will give you a really good overview of the material that you're covering this week with Chuck and the other lecturers. And I'll just digress shortly for one sidebar. Is it a marine heat wave, one word, or a heat wave, 2 words? And I'm a strong advocate for heat wave as a single word, partly because when a field evolves, we make up new terms and we put things together and make compound words. And so I'm a pretty strong advocate for marine heat wave as a single word. In a maturing field like marine heatwave research, the research community ought to be able to use consistent terminology. And at the moment, we're not quite there. Of all of the publications I could find that covered marine heat waves in their title or abstract, 148 used the 2-word heat wave, 500 or so, nearly 600 are using heat wave as a compound word. And you can see that that's increased over time. So in your research and in your publishing, please try and stick with a single word. It definitely makes meta-analysis a whole bunch easier. And some of the resistance to this has actually come from journals or from publishers who say our style guide has heat wave as 2 words. And so I've also been getting style guides changed for different journals to make it easier. And I'll give you the analogy. In Australia, bushfire is a compound word. It describes an extreme event. And that's overwhelmingly used as a description of how to talk about a bushfire. Earthquake's a single word describing a disaster. We don't use the 2-word version of earthquake anymore, even though that's how it originated. That's basically 100% usage around the world as a single word. And so again, stick with marine heat wave as a single word. Doesn't work all the way. Climate change is still 2 words, but maybe in future we'll see climate change become a compound word. So marine heat waves then have had this people noticing these really hot periods. And so again, 2003 was really the first description of heat waves as an event. Prior to that, people had described heat waves as hot water associated with things like El Nino in the Eastern Pacific. And so again, 3 really formative events, I think, in the Mediterranean, in Western Australia in 2011, and then the Gulf of Maine heat wave in 2012. And they really got the interest going of some of the community that you're hearing from today, like Andy Pershing working at the Gulf of Maine during this period of time in 2012. So what did we know in 2011? We did know that heat waves, which occurred in the atmosphere, were really extreme warm events that persist for extended periods of time. And on land, they can really have disastrous consequences. And again, that idea that the atmosphere as a result of climate change was giving us really strong extremes that had massive impacts on communities, I think also helped give this research field extra impetus. Heat waves were being described on land, but equivalent events were not being identified in the ocean. Again, we were associating warm water typically with large climate drivers. The first publication that used the word marine heat waves used the 3-word version, marine heat wave, and it was a research publication in very rapid time in response to this Western Australian event in 2011. And so that's the very first one we can find that uses marine heat wave. We now know over that period of time since then that marine heat waves have very dramatic impacts on things like changes in range, animals moving to new locations, or habitats being impacted. In the case of the top right, lush kelp forest transitioning into bare rock and rubble, seagrass being impacted on the lower right-hand side. However, at this time, we lacked a global understanding about the distribution, frequency, intensity, or duration of marine heat waves, or the underlying physical cause. And as you'll learn during this week, there are a range of physical causes. Another way of thinking about the field as well is through the topic areas rather than the literature areas. And so during the week, you'll hear things about climate drivers and how they influence marine heat waves, the regional processes and historical reanalysis on the left-hand side. You'll learn about ocean processes and the atmospheric contribution to marine heat waves. I hope there'll be some discussion of real-time monitoring and how important that is for people responding to marine heat waves. I'll finish on Friday with a second discussion around how to communicate around marine heat waves and help people prepare for adaptation and intervention. And then finally on the bottom is the prediction timescales. At the moment, we've probably had more prediction out years and decades ahead of time, but increasingly looking at prediction on seasonal timescales and even daily timescales. Really important for people who are going to respond to marine heat waves to have that shorter forecast period. So again, during the week, think about how you're populating this kind of diagram and thinking about the areas of research and where the gaps are. So I already talked about the Marine Heat Waves Working Group, but 2 really influential papers out of this group were the first one, which was 2016 about defining marine heat waves, and then a second paper in 2018 that built on this by adding a categorization scheme. At this first workshop in 2014, and in preparation leading up to it, we thought it was important to qualitatively define a marine heat wave. And a qualitative definition really sets the scene for a quantitative definition. The important things that we thought about qualitatively defining a marine heat wave were generally that it was discrete, it had a beginning and an end, it was prolonged, and it was anomalously warm for the location. We didn't want an absolute definition of marine heat wave, such as it had to be 2 or 3 degrees above average. It had to be warm for the particular location. We wanted a definition that would be flexible. It wasn't limited to the time of year. It could work in the subsurface. It could be applied to different data products. It could describe various types of marine heat wave, and it would encourage consistency in quantitative measures. After having arrived at a quantitative definition, we were then able to think about quantitatively define a marine heat wave. And that was always based on this qualitative definition. So what's anomalously warm mean? We settled on that it must lie above a high percentile calculated from a baseline climatology. And the choice of 90% is somewhat arbitrary. But because we're defining marine heat waves on a statistical basis, you need to have enough data to describe what's unusually hot and what's normal. And so a 90th percentile cutoff gives you enough data to robustly define a threshold. It should have a common baseline, for example, a 30-year baseline or a 20-year baseline, if possible. The heat wave should last for a certain period of time, and the period we selected was 5 days. Again, that's kind of arbitrary. In the atmosphere, 3 days was being used as a definition of a marine heat wave, and the ocean has a slower response time and a longer memory. So we thought that heat waves in the ocean should be defined as lasting a little bit longer to distinguish them from heat spikes. And we tested that to see what was the difference if we used 4 days, 5 days, 6 days, 7 days, 8 days. And it's not very sensitive to that choice of 5 days. And so in some sense, 5 days is good enough. The marine heat wave had to be discrete. It had to have clear start and end dates. And because sometimes data collection can be noisy, if it was a short gap between long events, we said that should be considered a single event. And that's implemented in the code for marine heat waves. So then we created a set of metrics out of that description. And here again in the figure A shows you a distribution of temperature at a location and a 90th percentile value giving us the threshold. If you then look through time on the right-hand side in figure B, you'll see you've got in the blue line a climatology for a region. The red is the observed temperatures, and the dashed black line is the threshold, the 90th percentile threshold. And once you've done that, you can then create all of these metrics from that description on the left-hand side. A heat spike is a very short event, but if you're longer than 5 days above the threshold value, then you've got a time of it starts and a time that it ends. You can have a maximum value. You can have the cumulative intensity. You can look at the slope of the temperature time signal to get the onset or decline rate. And so it's kind of a very rich set of metrics that can let you explore the differences in a marine heat wave. And so this definition also let you distinguish different styles of marine heat waves. And I don't think enough has been made of this. And you might imagine that each one of these might have a very different effect on the biology of the area. You can have symmetric heat waves in figure A, fast onset in figure B, where the rate of temperature increases very rapidly. In C, in the middle, you can have a slow onset where temperature increases fairly slowly before it peaks. You could have a short, high-intensity heat wave. And then similarly in D, kind of low intensity, but lasts for quite a long time. And each of the metrics there distinguishes those ones and makes them unique cases. So now that you have a definition, what does it allow you to do? And these are 9 advantages of having a consistent definition. The biggest one for me is that you can do comparison between different regions of the world, and my study can be easily compared to one that Chuck might do or that Andy might do in a different region. And so that comparison aspect, I think, was really important. It allows you to do detailed description of events in an area, and different parts of the ocean have now, scientists have now produced atlases of marine heat waves. It lets you look at the flavors of marine heat waves, and the flavors were just what I showed you here on an example there of 5 different types of marine heat wave that can be distinguished. You can look at the drivers of marine heat waves based on their definition. You can attribute marine heat waves to climate change, for example, or natural variability. You're able to look at trends in historical or in projections. They're really important for communication, and it's been a great area for communicating to the public how climate change is really affecting the ocean. And finally, the use of the definition is letting us make short-term predictions now. I'll go through quick examples of these, and I think from looking at the syllabus for the course, you'll hear more about several of these. So here's comparison of marine heat waves across regions. Let's compare Western Australia in the first column, the Mediterranean 2003 in the second column, and the Northwest Atlantic in the third column. And you can see in the second row, here's the consistent look at how strong those different events were and what time of year they occurred. And in the histogram plots below that, you can see how the current event compares to all other events that you've ever seen in that region. And so you can get a sense of how strong particular events were. And that comparative approach, I think, is really powerful. You can now extract many, many time series for regions around the world and look at heat waves over a long period of time. The second one is generating detailed descriptions. And again, here's an example of a marine heat wave atlas we've produced for Eastern Tasmania with looking at 12 different regions off the coast, identifying 400 different events and looking at what their kind of patterns are in space and time. And that revealed, for example, different types of marine heat wave flavors. And so on the right-hand side is a statistical analysis of the spatial marine heat wave patterns that are influenced by the ocean in the X direction and by the ocean in the Y direction. And so if the atmosphere influence is very high and the East Australia current influence is very high, we get heat waves that look like the upper right-hand one. On the lower left-hand side, if the air temperature influence is not very much and the East Australian current is not very much, that's what the heat wave pattern looks like here. And the arrows on these show different circulation patterns. So there's lots of interpretation you can do by looking at the flavors of marine heat waves because they'll have different impacts on biology. And I know that Marlon and Steve have been talking to you already perhaps about the difference of why don't all heat waves have the same impact on biology? And partly it's because they've got different flavors for what look like the same metrics. Yeah, I think that's it. You can make different statistics out of these flavors and then have different descriptions that give you a much greater ability to understand the biological response. A fourth area that has been able to be undertaken now that you have a consistent definition of marine heat waves is looking at the drivers of marine heat waves. And for example, the pictures on the right-hand side, these, I think there must be a nicer name than vomit plots, but we generally call them vomit plots. You can see where in the ocean the dominant driver of marine heat waves are. So the strong green, the driver here is ENSO related in the Eastern Tropical Pacific. In the Indian Ocean, it's a thing called the Indian Ocean dipole, gives a strong relationship with marine heat wave occurrence. And so the top panel showed us when you had more marine heat waves, and the lower panel shows you when you have less marine heat waves. And so these in a way start to give you some kind of ability to forecast heat waves as well, because if you're in that particular climate state, you might think about higher or lower incidence of marine heat waves. The vomit part of the plot, though, suggests that it's really noisy in some areas. And that's because in these plots, you just had to pick a single dominant driver, but there may be multiple drivers in a region. And these plots don't show that very well. Marine heat waves, as you know, have a variety of mechanisms of forming. And this work that we then did exposed the difference of heat wave formation when it was due to advection or when it was due to atmospheric heat input. And those two sources of heat into the ocean make a big difference on the biological response. So what kind of things are still to be done with the drivers of marine heat waves understanding? We understand some of these processes very well and some not very well at all. And then some of the marine heat wave drivers lead to heat waves that have very big impacts. And then some of the heat wave drivers also give us a better ability to predict. So I think there's a lot of work to be done around the drivers of heat waves and how we can use those for understanding the impacts and then the predictability of heat wave events. I'm moving to the fifth topic, which is around attribution. And so prior to about 2004 or so, technically, and probably even today, a journalist will ask a question like, was this flood due to climate change? And the scientist prior to 2004, very careful people would say something like, no individual event is caused by climate change. However, this type of event is likely to be more frequent under global warming. And the journalists would go away unhappy and the science that they'd stayed in a safe space. Thank you, that was very helpful. But attribution has been possible for almost 20 years now. And the first study that I came across was about attributing the European heat wave and working out whether that would have occurred with or without climate change. And so since then, scientists can now blame individual natural disasters on climate change using attribution methods. And so, for example, with marine heat waves, we can look at particular events, for example, the Tasman Sea marine heat wave of 2015-2016, and look at an event that lasted for 250 days with an intensity of 2.9 degrees above the baseline. How much more likely was that as a result of climate change? And the attribution study showed that it was 330 times more likely to have lasted as long as it did, and 6.8 times more likely to have got as hot as it did because of human-induced climate change. So we can definitely say for individual events now, how much more likely they are due to climate change. A really important thing for communicating. And so for different events now around the world, this kind of work has been done by a handful of people. So Northern Australia, a heat wave in 2016 was 8.5 times more likely to be as hot, and the length of time was 53 times more likely because of climate change. A really big one in the Bering Sea, about 7 times more likely in intensity and duration because of climate change. Again, some of these papers are there to read in the materials for the course. Okay, the sixth advantage is that you've been able to look at trends in marine heat waves. And so, for example, this plot here led in a paper led by Eric Oliver shows the annual number of marine heat wave days globally over the past 30 years of the record, with the El Nino and La Nina years mapped onto it. And so you've been able to see an increase in marine heat wave days over time. And again, that's where the really common statistic, compared to a common baseline, the frequency of marine heat waves has increased by 34%, the duration is 17% longer, and the number of heat wave days in an area has gone up by 54% over that record time. And so those are the three most common metrics that people use in marine heat wave work: the frequency, the duration, and the intensity. But here's the problem that people have pointed out. If you're using a common baseline to explain marine heat waves and define them, and the planet and the ocean are also getting hotter, pretty soon every day would be a marine heat wave day. And so is that a useful term? Is that a useful description if every day is a marine heat wave day? For example, this analysis here showed that by the year 2050, you'd have almost 300 days of marine heat wave in some parts of the ocean. And so what were the options? You could change the definition from the 90th percentile to say the 99th percentile. You could change the baseline period, and so you could continue to update the period of time over which you calculated marine heat wave change, or you could create a category system. And at the time, the heatwave group I was working with decided that we think creating a category system was most useful because it would be a really effective communication tool to show that heat waves would still be more common in the future and we would experience stronger and stronger events. If you update the baseline, you'll have the same number of heat waves in the future as you do today, and that might not be a very effective way of communicating climate change. So the design criteria, in the same way as we work through qualitative explanations for marine heat waves, the qualitative way of designing a categorization scheme, we wanted it to have these features. You wanted to be able to describe and update the category as the marine heat wave progressed. Given these things were lasting 200 days, you didn't want a system that said, we can't tell you how big it is until the event's finished. You want to be able to have that updatable as it goes. The categorization should represent the local effect. It should be possible to change the category over time as events strengthen and weaken. And the metric shouldn't be overly complicated because we really have a very strong communication goal in talking about marine heat waves. And so just as cyclones or hurricanes have a category scale that can be instantaneously reported. In this case, my storm began as category 3, intensified to category 4, then went to category 5, then relaxed back to category 2 and 1. That was a really nice model that we adopted. And so the categories of marine heat waves that we suggest based on the definition in the 2016 paper would just be based on multiples of the 90th percentile. It's an instantaneous measure. You can see the dotted line representing an observed heat wave, begins at category 1, moves through category 2 and so on, and then relaxes again out of the heat wave condition. It's instantaneous, and this categorization system is expandable. At the moment, where commonly occurring heat waves go up to category 3, there aren't very many category 4. As the planet warms, we might need to add category 5, 6, 7, and so on. And so this is one way of reflecting how much change there has been in the ocean as a result of climate change. And so, for example, this is what it looked like for the Tasman Sea. Here's a common marine heat wave again that I work a lot on, the Tasman Sea 2015-16 event. It had a maximum intensity of 2.7 degrees. It lasted for 252 days, and it was in category 1, the moderate category, for 59% of the time, and as strong in 41%. And here's when it was in those different categories, as you can see from the color here. So a really effective way of describing the intensity changes through a marine heat wave period. In the North Pacific blob, again, you can see this was moderate for 44% of the time, strong for 43%, and it was in category 3, the severe, for 13% of the time, down here during the winter months in February 2015. And really how we hoped it would be used is in talking with people who are interested in events. And so if you had been tracking the Northwest Atlantic marine heat wave in 2012, you would have been able to see right now it's a category 1 event, then a little bit of category 2 showing up. As we got into the summer months, it became category 3. And we're out. So that's a really powerful communication to be able to have with journalists and media who are interested in these evolving events. There's another example where a marine heat wave was an extreme heat wave, but only for 12% of the time. And so what do you expect the biological impact to be, depending upon how much time you spent in each one of these states? And so the category is another metric that you can use to investigate the biological impact. We can then look at how the trends in the categories have changed over time. And for example, between 2016 and 1982, which were 2 very strong El Nino years, you can see how much more area of the ocean was in strong marine heat waves in 2016, more of the orange color, compared to 1982. And again, there's been a 24% increase over the last 30 years in strong category 2 marine heat waves. And that's very similar analysis to that people are trying to do with cyclones and hurricanes. So the 7th area is being able to do projections of marine heat waves. And again, using 2 different climate scenarios. For example, a representative concentration pathway 4.5 shows that by the year 2050 or so, we'll have very many extreme heat waves, but we'll have an increasing number of strong and severe heat waves. If you use the 8.5 scenario, which is the most extreme, and I hope we're not on that trajectory anymore, you can see that we start to have many more extreme marine heat waves towards the end of the century. Finally, just a sidebar about how we should name marine heat waves, again, for more communication. And so this table says for a bunch of disasters that we have, extreme events, the 2 options are that they do have a category or they don't have a category on the left-hand side, and they do have formal names or they don't have formal names on the 2 columns. And so things like hurricanes are measured on a scale and given a name. So it's something like Hurricane Katrina, a category 5. And that's a very clear communication. And so at the time we began working on it, marine heat waves were in the lower right-hand corner. There was no category and there was no formal naming. And so that made it very difficult when people wrote about them to for others to recognize or remember those events. Things like without formal names, atmospheric heat waves don't have very formal names, but that's now changing. But they do have a category and a scale. And in the other case, there are some things that don't have a category or a scale, but do get names. So in Australia, we name bushfires, really extreme bushfires, by the day, the week they occurred. So we have had a Black Saturday bushfire, a Black Tuesday, a Black Thursday. In fact, after you've had 7 of them, you run out of options for calling them by the day of the week. So that's a slight problem with that. So our recommendation for naming marine heat waves is that you give it the area and the peak year for strong marine heat waves, at least category 2. So a name like the Tasman Sea 2015, it tells me where it was and what year it occurred. And those can be really useful, again, for us talking and communicating around the planet. I will say that things like Hurricane Katrina, while it has a name, it's really hard to remember the year that it occurred if you weren't in that exact location. So something about a year in giving a name is a pretty important feature, I think. I think now we've moved marine heat waves into that upper left-hand corner, where they now have a category and you can have kind of formal naming that we can use to describe these events. And that's all become much easier for journalists and researchers to use with a tool that we've built called the Marine Heatwave Tracker, which lets you click on any pixel in the ocean and extract a time series of marine heat waves for that event. This website, which you may play with during the course, also lets you look at cold spells, which are the cold equivalent of marine heat waves. And it's been really useful for doing really rapid analysis of heat waves. And you can extract the raw data using this website also. Finally, the frontier for me is in forecasting marine heat waves. We can forecast in a variety of ways. The first technique is using an expert model. That's your experience or the use of a climate driver. This year, it's a La Nina year. In this region of the ocean, heat waves occur more commonly with La Ninas. And so that experts or analog forecasting is a way that you can still get pretty good predictions for some regions. The second way is using statistical models, which are based on the historical data. And so statistical tests like additive models are one way of producing a forecast. Machine learning would lie in this domain as well. And so give a machine learning algorithm a bunch of historical data and ask it to make predictions is one possibility. The third one is using dynamical models, either ocean-only models or models that are coupled between the ocean and the atmosphere. And those ones are nice because they actually represent the processes. And so you can produce future projections even if the history has never experienced that kind of condition because the model is process-based. It's really important that you do the skill assessment of the forecast and the uncertainty, but I won't touch on that today. And so, for example, my team in Australia is now producing dynamical marine heat wave forecasts. That's using a coupled ocean atmosphere model, and we're able to produce forecasts about 3 months ahead of time. And for example, here's one that was produced in January earlier. Sorry, it was for January this year, and it was produced in October in 2023. And that was predicting not much heat waves around northwest or northeast Australia, but stuff through the Indonesian archipelago. We used these a lot in the last year because forecasting is really helpful for people who are preparing to cope with an extreme event. In this schematic here, a heat wave has begun where I've indicated with time start. And if a heat wave has begun, then anybody who's being impacted just has a reaction period of time. They're just trying to do something about it once the event has already begun. If you can do a forecast sometime earlier, then you introduce a preparation window, and you've got a period of time before the event occurs to do something about it. If I'm growing fish in an aquaculture cage that's going to get hot, I could choose to harvest the fish early. I could change their food mix. I might even be able to move the fish cage to a cooler area where there's more upwelling. And so depending on how long your forecast is, you give people a whole bunch of options in responding to marine heat waves. That kind of forecasting matters a lot because, as we've seen, marine heat waves can cause billions of dollars in damage. And while I don't think forecasting will allow you to avoid all of the damages, I definitely think with forecasting, you'll be able to reduce some of the impacts, just as we can with forecasting cyclones or hurricanes on land. So anytime you have a forecast, some people will be able to do something to avoid a loss. More recently, we've also shown that there might be a link between marine heat waves and cyclones. And so that's a very dramatic way of showing that understanding the ocean dynamics will have a very big impact on human well-being and even lives. And so, for example, a marine heat wave will supply energy to the atmosphere that can supercharge a hurricane or a cyclone. Similarly, if there's lots of mixing, the ocean can actually interrupt the formation of a cyclone or a hurricane. And so if you've got areas where you've got a marine heat wave in very deep warm water, you may actually increase the intensity of cyclones. I'm going to talk more on Friday this week, my Friday, your Thursday afternoon, on how to use forecasts and responding to those ones. But in particular, thinking about if you can do the forecast of these climate risks on the left-hand side, how you then help people who are responsible for their for businesses like seafood or tourism or coral reef restoration or protected species work, how to use forecasts there. And I'll talk more about that on later in your week. I will just remind you that all of the code to do the kind of heatwave metrics that I've talked about here has been publicly available for more than, getting close to 10 years now. And so there's both R code and Python package that you can download and manipulate to run your own analyses for marine heat waves. And while that's based on the definitions that me and my group have worked on, you can change any of the numbers in the code to explore different options. So the code is flexible to you trying different applications for different purposes. And again, it does also do cold spells in this series, in this code. Alrighty, so I'll finish up by saying, the marine heat wave motivation for me is a chance for fast learning. It's a real stress test on our systems for managing the ocean sustainably. And if we can better prepare for managing stress today, maybe we'll be in a better position for coping with long-term climate change. I've talked a lot about how having a consistent description has really allowed comparison of heat waves and really fast learning. And I really think that while there are a number of definitions around, consistency has really allowed this field to move very rapidly. We do need continued research to address the relationship with impacts. Every heat wave doesn't have the same effect on the biology, even if the intensity of the heat wave is the same. It can depend on where in the species range the heat wave occurs. It can depend on whether there was a heat wave last year as well as this year, and a whole bunch of other things that really make this relationship with impacts really hard to discern at the moment. And for me and my group, a prediction of marine heat waves is the current frontier. Being able to make a prediction about whether a heat wave will occur in 3 or 4 months ahead of time is a really powerful thing, and it's a pretty amazing area to be working. And I'm pretty sure that is my last slide. It is. So I will probably stop sharing that one and look at your faces and see if there's any discussion or questions.
That was really great. Thank you very much, Alistair. I think we're going to try to let people ask questions here, and people can also send them in the chat. We'll do it for a little while and see how well that works here. It's always something new.
Yeah, beauty. And Chuck, will you either confirm or caveat my suggestion that we'd hear more about these different topics during the week, right?
Absolutely, yes. And we've also, I don't know if I heard from you, but we recorded these, and I'm hoping that we can share your presentation, the recording, on we're going to have a YouTube channel.
Yeah, beauty.
Okay, good. Okay, yeah, I'm trying to think of the best way to do it. And here, just raise your hand. So why don't you go ahead?
Chuck, we have a microphone we can pass around.
Oh, okay.
There we go. It should be connected.
Test.
Yep, gotcha.
Hi, Alistair. Okay.
Sorry, that is.
Hi, so can you hear me?
Yes, I can.
Okay, awesome. Thank you for your great talk. So I think you kind of brought up a really interesting topic about like categorizing marine heat waves, and that was kind of something I was really kind of thinking about that you mentioned, especially I think your last slide was talking about hurricanes and the impact of marine heat waves and how they could potentially impact, recently in San Diego, we had a hurricane that came up. And generally the convention is, we have a cold current and we have strong wind shear, so hurricanes typically don't impact. But, we a couple summers ago had the Baja warming event, kind of like a indirect implication of the blob event. And so I guess I was wondering, in your definition of like categorizing heat waves, have you guys considered depth of like the heat wave? I saw that you had that as one of your variables, but I was wondering, because the blob event was very different from the Baja event, and I'm assuming the event you showed in Australia was a vastly different event. So I'm wondering kind of like how you were categorizing hurricanes, right? If depth would be what would be considered wind speed, I guess, or something for hurricanes. I guess I'm trying to equate the two, but
Yeah.
I guess, have you guys
Yeah.
explored that at all?
Yeah, so the metrics out of the basic definition are two-dimensional metrics. They don't consider the depth, but you can apply the heat wave metrics to different depths, or even better still, you can apply them to a measure called heat content or mixed layer depth. And so that's really the measure you want for hurricane cyclogenesis, is how much heat is in that upper ocean. Because if the heat wave is shallow, it's more likely that the hurricane will disrupt the heat wave. If the heat wave is very thick, it's more likely the heat wave will supercharge the hurricane. And so I think expanding our definitions to be able to get, a bulk measure of the energy available in the ocean in these heat waves is a really important step to make. But my current definition doesn't do very well 3D in either, area or in depth. And so they're real areas for improvement. And I will just say, what's the advantage of forecasting? At the moment, a hurricane, you can forecast a hurricane maybe a week ahead of time. But if we could forecast the marine heat waves in an area 3 months ahead of time, you kind of start to build yourself a composite forecast that says actually our hurricane risk might be elevated. And so you might have a 3-month warning because of the amount of heat in the ocean. If we get a hurricane, it's going to supercharge.
Thank you.
Thanks.
Hi, Alistair. Hi, sorry. Hi, Alistair. Thanks for the talk. Have you considered using altimetry as an additional input of information on the three-dimensional kind of aspects of a blob or a heat wave?
Yeah, that's a great suggestion. At the moment, I tend to do most of my work with 3D ocean models where they've been basically reconstructed temperatures at depth. So I use the ocean model for that information. But using altimetry data would be awesome because you could do it in real time based on, the sea surface height telling you something about the, the mixed layer depth or the change in the vertical structure. So I reckon that there's a really great bit of research to be done around using altimetry data to better characterize marine heat waves. And I'm not aware of anyone who's doing that.
Hi, this was great. Oh, it's weird to hear myself talk. Okay. Thanks for your talk. I was actually curious about the question Anthony just asked related to depth. And earlier we learned from Bruce, the importance of having in situ measurements and all the places in the world where we're missing in situ measurements over the water column. And I was wondering if you were going to, put out temperature sensors in the ocean, and selfishly, I'm kind of thinking about like from a long-term ecological monitoring perspective, at which depth would you kind of start to lose predictive capacity? Like at what depth, from a modeling perspective, is it really helpful to have temperature data from? Obviously, it'd be great if we could have temperature data from every meter in the water column, or really high resolution. But if you only have fixed resources to measure so much, at what depth do you start to lose predictive capacity for modeling or predicting these marine heat waves?
I'm going to partly sidestep your question by saying that I don't understand yet where the predictability comes from at depth, but only to say that a depth understanding is really important. And probably you need to go as deep in the ocean as that feature can then come back to influence the surface. And so you might learn that sometimes the blob held a very large volume of warm water at depth. And so even though the surface signal disappeared, it was very easy to recharge that event the following summer because heat was still stored deeper in the ocean. And so you need to measure as deep as the heat is being stored. But we do have not only moorings, we've got an observation network around the globe called Argo, which is profiling floats that go down to about 2,000 meters in depth. And that's plenty deep enough. So we can use that array. And then on the continental shelf, typically moorings in place will go to 200 meters or so. If I had to pick a single number, I'd say you need to be going to about 400 meters, because sometimes the mix layer gets down towards 200 or 300 meters, and that's where we want to understand where heat is being stored. Chuck or any others, you want to inject on that question? I think it's a really interesting one, and I don't feel I had a very much experience with answering it.
So can you hear me when I'm using mine? Yeah.
Yeah.
So I'm not sure I can answer that, but one of the things that's related to it that I find rather interesting is, in our example in the Gulf of Maine, where we're looking at this slope water, this warm slope water that enters into the deep basins, a lot of the definitions of marine heat waves are sort of based on sea surface temperatures. And, using the way you define a heat wave, the heat waves that we've seen in the deep waters of the Gulf of Maine may be years in length, as opposed to, weeks or months in length. And so it's going to be really interesting when we start to, in areas where we actually have good measurements of deep water and we have these advective events bringing in water that, these heat waves are going to be characterized by much longer durations than often we see it with sea surface temperature. So I think that'll be a fun thing for us to explore going on. And it's somewhat related to this question, in that, we've kind of, the evolution of this field is sort of developed from our wonderful capability of measuring sea surface temperatures. But we now recognize, particularly in areas where the deep waters are being warmed, that they can actually basically precondition the whole system so that it enables heat fluxes to that might not have otherwise created a marine heat wave at the surface to now be sort of set up to do that. And I think that's going to be a really exciting area. And so coupling the deep water with the surface is going to be a really interesting area, I think, in the next decade. Yeah.
I use an analogy. Actually, my kids are in primary school, and so I've talked to their school about heat waves, funny enough. It's an analogy of it's a heat monster. It's either hiding in the clouds and it's coming down to hit the ocean. It's either running from the north or south, and it's a monster coming over the fields to that particular location, or it's hiding in the deep sea and it's coming up. And so we've got these three mechanisms of where ocean heat come from. And I think we've really underdone the monster that hides in the deep sea, preparing it for those hot conditions.
Well, we'll be visiting that tomorrow, I know, and maybe some other times. But anyway, that was great. Is there anybody else? Yeah. Okay, we have additional questions here. I'm going to shut my computer down for a sec.
Super. Thank you so much for that presentation. Really interesting. And I especially appreciated the discussion about the different categories of marine heat waves, especially as someone who's relatively new to the marine heat wave world. I was just wondering if you could speak briefly about your experience communicating to non-science audiences about marine heat waves. Have you found, I'm thinking policymakers, also general audiences, have you found that there's growing interest? Are people receptive? Are these categories digestible? And then maybe part two, do you have any tips for early career researchers, which is primarily who's in the room and also on the call, for sharing marine heat wave research and findings? Are there anything we should be especially aware of, or maybe some soft spots to be aware of for other audiences? Thank you.
Thanks, Olivia. I'd say that some of the greatest critics of this work are physical oceanographers who say, we've always had hot water in the ocean. All you've done is describe it in a different way. And that's a fair criticism. We've just given a name to something that was already there. But the naming and the categories were really important for communication. I think if we hadn't given a definition and we didn't have categories, communication would be a lot harder. And even the base definition of Olivia uses words like maximum duration, intensity, return time, things like that, rate of increase. They're kind of hard for, or even not very interesting to journalists. But being able to say it's a category 4 event, that's a really strong thing happening off our coastline right now. They're really easy concepts. And so I think that my advice for early career is don't try and be clever, try and be simple. And the simpler you can make something, the more people will understand it. And unfortunately, science has sometimes rewarded people who worked on very complex things and made them very complex. I hope you try and make things really simple, because the more people that can understand this, the better our planet will be. And so, yes, shamelessly, the design of the categories mimicked hurricane categories because the world already knows those. Using that same language has also allowed really easy penetration into journalists and classrooms and other non-specialists. It's not without controversy, and maybe during the week you'll hear people talk about, should we have a shifting baseline, and what does that mean for understanding heat waves in the future? But for heat waves today, even describing them as different categories has really been very, very powerful. Thanks, Olivia.
Let me just mention to everybody and Olivia that Alistair will be coming back later in the week, and he'll be addressing specifically communications, and there's a paper in our reading list specifically about how to do this. So we will hear more on that subject. Your comment, Alistair, about physical oceanographers being sort of poo-pooing it, like, well, what are you doing new here? It reminds me when I first got into my geosciences department, and I was like the only oceanographer, and a lot of them were old school kind of plate tectonics people, and they really were not very receptive to climate change. It's like, well, the Earth's climate's been changing forever, right? And
yeah,
it's like, yeah, but the difference was we weren't doing it right. So anyway, it's interesting to see how different fields, different disciplines respond to new fields of research.
Alistair, I have a
wait a sec. Okay.
I have a comeback you can give to these physical oceanographers and say, we've always had global circulation. Conveyor belt circulation is just the same thing told in a simpler way. And but it's taken physical oceanography a long ways by using that little 2-syllable, well, more than 2 syllables, but 2-word shorthand for global circulation.
So you're trying to start a fight.
Yeah, trying to start a fight.
Yeah. Hey, but as I said, my motivation for doing this work is really through a climate lens, and extreme events are this window to the future. And it's the studying of them and the communication of them that I hope will rally people to behave differently. And so I am, I suppose, open in saying that the communication part of it and the language choice is really a big part of how I pitch the research. And it is, marketing makes it sound too glib, but it's definitely thinking about your end user is not other researchers. It's other people making decisions in society.
Well, I think we've had all the questions from this group here, and I don't see any in the chat right now. So thank you again, Alistair. That was really superb, and we're really looking forward to hearing your follow-up on Friday about how to communicate to the rest of the world in detail.
Yeah, beauty. It's really fun. Thanks for the opportunity, Chuck. And I know you're at the end of your day, but I'm just starting mine, so I'm still excited after this. Thank you.
Good. All right, I'm going to end.